Syzygy episode 45, Dark Energy and the End of the Universe. And welcome back for another edition of the Syzygy podcast. Joining me as ever, sitting opposite me at the table here in her office, Dr. Emily Brunsden. Hi, Emily.
Hello, hello.
So this week we've got a big one, and I'm looking at your board. You just completely thrown me, Emily. Normally, okay, behind Emily here in her office, there is a whiteboard, right? She sits at the table and behind is a whiteboard. And on that whiteboard, for as long as I can remember, there has been a long list of, here are all the topics that we need to talk about on Syzygy. And we sort of every once in a while cross one off and usually add a couple more underneath it. And it never gets any shorter. And it's gone!
It's not quite gone, to be fair. I just needed to clean the whiteboard.
Oh, thank goodness
for
that.
I took a photo.
I thought our lifeline was...
They will go up, and they'll go up in much neater handwriting, I think, this time.
You just scared me for a second. And the reason that I was looking at the board was because for the longest time there's been this one item in that list that we've been saying we really ought to talk about this one day. Because every once in a while in the podcast we'd sort of touch on this thing and then go, but we don't have time to talk about that. It's such a big topic and such a complex and interesting and fascinating topic. But we just haven't tackled it before. And it was always sitting there on the list waiting to be crossed off. And that is the topic of dark energy and the increasing expansion of the universe, the acceleration of the universe. And that's a big topic. And we're going to delve into that today, at last, finally. Very exciting. Looking forward to that one. But before we do, we've got a bit of news. Pretty exciting on the social medias at the moment. We are getting involved in a little thing called the Podcast Social Club. It's a podcast festival going on up here in Yorkshire at, everyone knows, the centre of the podcast galaxy, which is the city of Thirsk. Is it a city? I don't know if Thirsk even...
City might be pushing it a little bit.
It's not a village. Anyway, it's in Thirsk, and it's coming up on the 22nd, 23rd of November, and we're going to be a part of it. We are doing a live podcast show on the evening of Friday, the 22nd of November. If you want to take part in that, if you want to come along and be part of the audience for that show, go to podcastsocialclub.com. Go and find us on there. Find us amongst all of the different podcasts that are going to be playing over that weekend. Book yourself a ticket and come along and join the audience. It's going to be a very fun night. Looking forward to that one greatly. So that's Friday, the 22nd of November. Now, we need to get into something.
Yes.
Emily, what are we talking about? How are we going to do this?
So, I think we should start off by looking at dark energy from just a very straightforward definition of what it is. And basically, it's an unknown form of energy that causes the expansion of the universe to accelerate.
Right. There's a lot to pull apart there. We often talk on this show about unpacking things and figuring out what's inside them. There's a lot to unpack. There is a very large amount of baggage. This is a big suitcase. So we need to start somewhere.
Yes. Well, let's just start by upfront saying dark energy should not be confused with dark matter.
No, very different crowbar separation between the two. And let's have a look very broad scale at what is the universe made up of, right? We tend to think of the universe as being made up of matter, of stuff, right? The atoms that we see around us and the light that we see around us in the universe, the other the matter particles and the force particles and so on. And we see planets and we see stars and we see galaxies and nebulae and all sorts of stuff in the universe. And embarrassingly, that's actually only a very, very small amount of the actual stuff in the universe, isn't it?
Yep. Everything that we can see and touch, like galaxies and stars, comes to about 5%.
5% of all of the energy and matter and stuff in the universe, right? Put all of that together, add it all up in the big cosmic ledger, and that's 5%.
It's pretty pathetic.
Okay, so the next biggest stuff is dark matter.
Dark matter, yes.
Right, and dark matter, we still don't know what it is.
Not exactly.
No, we're getting a little bit of a grip on it. We know it's there because we see gravitational effects in the universe, galaxies doing weird things that galaxies shouldn't do, and all of that sort of. Well, I'm not going to talk about that in great depth now. But dark matter makes up how much of the universe?
Something like 27%.
Right, so we've got 5% and 27%. That doesn't add up to 100 by quite a wide margin. Yeah, so we're talking something in the order of sort of 70-ish% of the universe is other, and that's what we call dark energy.
Yep.
And it's a little bit embarrassing, or not, exciting, inspiring, perhaps, to think that all of the stuff that astronomers have been studying for so long, the stuff that you can see, right? The stars, the planets, the galaxies, all of that is just such a tiny proportion of the universe. And the rest is dark and currently unknown, speculative. Who knows? A big shoulder shrug, but a lot of work going into it.
Yeah. So the names that dark matter and dark energy, they sort of sound the same, but there's no physical kind of relationship between them. They just happen to be called dark things because we're not very good at seeing them.
Yeah. I mean, it kind of makes sense. And dark matter was sort of postulated first, wasn't it?
Yes,
Dark matter was it Zwicky who came up with that one? I think he was the one who named dark matter.
Yeah, almost as kind of an off the cuff kind of facetious thing.
I don't know. It's probably matter of some kind, and we can't see it, so dark matter. But we're not talking about that. Crowbar separation between that and dark energy, which is a different thing.
Definitely,
so, talk to me about dark energy.
Okay, so let's come back to that definition. It's an unknown form of energy that causes the acceleration of the expansion of the universe. Mm-hmm. Let's go to start off by looking at the observations, because this is how we came across dark energy's existence. Was basically things started to not add up. And it was very much this acceleration of the expansion of the universe that really showed us that our maths didn't add up about what the universe was made of.
Yeah, it's one of these weird things in astronomy, in cosmology, where observations were made. It didn't make sense. So we need to throw something into the theories to make this work. But clearly there is something there. There is a need for dark energy, whatever that is. So let's go and have a look at that evidence. Yep. Where did it come from?
Okay, so the acceleration of the expansion of the universe means that we've known for quite a long time that the universe is expanding, right? Galaxies on the scale of galaxies, or at least on the scale of big clusters of galaxies, are getting further and further apart.
Yeah, we've known that for a long time.
Yeah, so that comes back to Hubble in 1929. So he first made those measurements. He saw that the furthest galaxies away from us are moving away from us the fastest, which if you are in a volume of space, this is a natural thing, that the galaxies that are close to you will be moving away slowly if your universe is expanding, and the ones that are furthest away from you will be moving fastest.
Yeah, and the notion of that being that it's not that the galaxies themselves are sort of whooshing away through space and they're all running away from us for some reason, they don't like us. It's that the space itself, the material of space-time, whatever that is itself expanding, and that's taking everything away from everything else, which from our viewpoint, here in our galaxy, makes it look like everything else is moving away from us. But under those conditions, that's where you would see the further away they are, there's more space between us and them, and so all of that space expanding means that galaxy looks like it's moving away even faster. So that's the expansion part.
Yeah. And the really nice, very traditional way of visualizing this is looking at bread. If you've got bread with raisins in it and you stand on a raisin inside the bread as it's baking and getting bigger, then it will look like all the other raisins in the bread are rushing away from you, the furthest ones moving the fastest.
Yes, whereas every raisin will feel the same way.
Exactly.
Every raisin feels like all the other raisins are not liking it and running away.
Exactly.
Yeah, so there's nothing special about us on our particular raisin.
And that was fine. We understood that those measurements that Hubble made really well, that we could say that the universe is expanding. Okay, that's fine. It does beg the question of why the universe should be expanding, because the one force that we had a great handle on at the time was gravity.
Yeah, and gravity is not an expanding thing. Gravity is a contracting thing. Gravity is pulling things together. It's keeping the Earth going around the sun and all of that sort of thing. So
yeah, if you've got two masses, then they will attract each other with gravity and they will come together.
Yeah, it's an attractive thing.
Yeah, so if you've got two galaxies, they will attract each other gravitationally and come together in the absence of any other forces. But the universe was measured to be expanding, and we could explain that. Well, if you think back to the Big Bang, maybe that's just an artifact from the kind of explosive nature of the Big Bang.
Well, I mean, that's where the whole notion of a Big Bang came from in the first place.
Exactly.
Was it not? That if things are expanding, then wind that clock back. Things must have been much closer together and much hotter sometime in the distant past. And if you wind that clock backwards, you get to something like 13.8 billion years ago.
Yep.
There was this almighty boom, which we call the Big Bang. But that's where that came from.
Exactly.
And we're just seeing the after effects of that. So, once you swallow the notion of 13.8 billion years ago, there was a Big Bang, then it kind of intuitively makes sense that maybe we're currently now living in the end throes of that expansion. Fine, no problem. I can see that, sure.
Yeah. And that's fine because, and remember, everything's a balance of forces. So just like when we talked about stars, we talked about how stars hold themselves up against the force of gravity by using the pressure from photons, by the energy that they're releasing through light. That's how they hold themselves up and don't collapse down.
Yeah, because gravity's pulling in really hard, and without something to push back against that, then the whole thing would just collapse down and you'd have black holes everywhere. So,
exactly.
It's this balance of forces.
Yeah,
Cool.
so in this case, the universe is holding itself up with this pressure that's being formed from the Big Bang.
Mm-hmm.
But we started to make better and better measurements. And this came through in the 1990s when we started to use a really important thing called a supernova explosion.
Yeah, now these things are great for measuring distances, aren't they?
Supernovas are fantastic.
And remind us of why that is again. There's something special about them.
They're so bright is the first thing. So a supernova is basically the death of a really, really huge star, massive implosion, huge explosion, lots and lots of light. And there's a particular type of supernova that, due to the way that it forms, basically is exactly the same brightness no matter where it occurs.
Right. It happens very, very much the same every single time.
Yeah.
Yeah.
It's basically got some constraints on it from physics. It says you have to be this bright if you're this type of supernova. And that's so useful because that helps us to measure distance very, very accurately. If you know how bright your light bulb is, it doesn't matter what distance you take it away from you. You know how far that is because you know how bright that light bulb is intrinsically.
Yeah.
And you measure how bright it appears to be to you.
Yeah. They give that a really nice name in astronomy, don't they? The standard
candle. Yeah.
Right.
So we know how bright the candle is. And so we can just measure how bright it appears to be to get the distance. So this measurement was done on an enormous scale in the 1990s. Honestly, it was a huge observational effort to get these measurements. And we were looking at using supernova to get distances of really, really far away, galaxies very, very precisely.
So observing, looking for signatures of supernovae. Because, I mean, they don't happen particularly often for any given collection of stars, but when you're looking at galaxies which have lots and lots and lots of stars in them all over the night sky, you must be seeing them all the time.
Yes, yeah. I mean, like even in our galaxy, we expect a big supernova of this type to go off pretty much once a year-ish.
Right. So big, as accurate as humanly possible measurement of a whole bunch of supernovae in a whole bunch of galaxies in order to really nail down this expansion of the universe. And just to be clear, they weren't looking for anything other than the universe is just expanding and probably slowing down as it winds out of the Big Bang 13.8 billion years ago.
That's the idea, yeah, because if you've got basically an amount of energy that Big Bang put into the universe, then that should be slowly decaying and gravity should slowly take over and basically become the dominant force.
Makes perfect sense. That's what they were expecting. Turns out.
But the measurements did not show this at all. The measurements showed that instead of just continuing either at the same rate of expansion all the time, or instead of even slowing down, in fact, over time, the universe is getting faster and faster in its expansion.
And that's weird. That's very, very weird because that suggests that sure, okay, wind back 13.8 billion years. You have a big explosion, wind forward, everything's still whooshing away, but gravity's pulling back and that'll slow down. This is suggesting that no, not at all. It's actually speeding up. And the only way that it could be speeding up is if there's something pushing everything further apart. Like the space is expanding faster.
Exactly.
Something's doing that.
You need something else. You need this extra energy, this extra push, basically, that's happening to push things apart faster and faster and faster and faster and faster.
And this came out of, at least initially, these studies, these observational studies in the 1990s.
Yep, 1998 was
it?
the big paper. Yeah.
Yeah.
Really
And that
exciting.
ultimately led to the Nobel Prize going for this discovery of the accelerating expansion of space in 2011, Nobel Prize for Physics, I think.
So quite a quick turnaround for a Nobel Prize.
Yeah.
So this is the first sort of ideas. Now, at this point, when we made these measurements, we just took out our old textbooks and we thought, okay, we've got to find an explanation for this. What is this push? And it turns out we already had a construct that could help us explain it. And this is still the number one kind of theory that's being pursued to understand dark energy. And there are lots of ways you can talk about and explain dark energy, and some of them are more fringe than others. But this is the sort of mainstream way, and it's definitely the way that you can fold in lots of the other ideas as well.
Yeah, I mean, if you're going to come across something like this, which is weird, didn't expect that, then probably the best approach to it is to go for the simplest option first and see how far you can get with that. And the simplest option in this case had been around, well, since the beginning of general relativity and that theory of gravity.
Yep. So dust off all those textbooks, go back to Einstein in the 1920s, and we've got an idea that we can use there.
Yeah. And that originally, like it was a solution to a completely different problem that actually then turned around and became quite apt.
Yeah.
At the time, when Einstein came up with his theory of general theory of relativity, I should say, it was considered that the universe was not expanding, that the universe was stable and always was and always will be this sort of very flat, non-moving thing. And yet Einstein's theory suggested that shouldn't really happen, that would either be contracting or expanding, unless you had this other special term in the mathematics, this constant thrown in.
So let's call this as a cosmological constant.
Yep.
You might see it called lambda as well. So it's a capital Greek letter lambda. So it's basically an upside down V. And this was the idea that we had this term basically in the equations. Einstein used it to balance everything in his universe and his gravitational equations so that you could have this static universe.
That was the theory of the universe at the time, was that everything was static and unchanging, and so the only way to do that was, well, we'll throw in this number here.
Yeah. And it's not completely out of nowhere either. I mean, the 1920s and 30s were such an exciting time for physics because another way you can talk about this cosmological constant is to think about it as a vacuum energy.
Right.
And what that means is it's the energy density of just a vacuum, empty space.
Nothing.
Now that sounds very counterintuitive.
Does sound a bit weird because surely a vacuum is nothing. That's the whole point of a vacuum.
But a vacuum can have an energy density that's kind of just this base level of energy that exists in space.
Yeah, it's allowed. It's weird, seems a bit weird, counterintuitive, but actually it's allowed in the theory.
Yeah, it's also very, very necessary in quantum mechanics to make things happen. It just turns out that their numbers are completely different to the cosmological ones. But
that's a whole other story.
We'll put that one aside. Everyone needs a vacuum energy, basically.
Yeah.
And so what this ends up being is, so Einstein put it in to get the static universe, but then as soon as Hubble's measurements came out, he sort of looked and thought, oh, you dunce.
Yeah, what an idiot.
Why did I think that the universe had to be static?
Yeah. Didn't he call it, like, at one point he called it his greatest mistake?
Greatest blunder,
Greatest blunder is to put in this thing to sort of force there to be a static universe. And then it turns out the universe isn't static. And he could have perhaps intuited, maybe we should go and look to see whether or not the universe is expanding.
Yeah.
Because my theory says that that's possible.
Because there's no reason why it shouldn't be static. No. If you take the concept of matter in the universe, we already know that matter is not evenly distributed throughout the universe. So if you have an overdensity of matter in one place, you have a lot of galaxies clustered in one bit of space, then they're going to have a local gravitational attraction, which is going to be really strong. And if you don't have another term to a more uniform term to balance this, then they're just going to collapse down and your universe is going to shrink down to nothing very quickly.
Yeah. So, I mean, I guess, hindsight is 20/20 and all of that. For the best part of 70 years, this term, this cosmological constant, was kind of just thrown out and kind of laughed at. I mean, I remember learning about it at university and it's like, oh, Einstein, you crazy guy, putting this thing in. How could you possibly think that you would need that term? We don't need it. The universe is expanding. So easy, done. Yeah. 70 years later, it comes back in vogue.
It comes back in, yeah.
Because these discoveries have been made that say, it's accelerating.
We need a new thing.
We need a term in the equations. Bring it back.
Yeah, so it's a really nice story, actually. And I'm sure Einstein would be super pleased.
Oh, he'd be laughing in his grave.
Come back, yeah. So it is really, and we know a bit more now about what the kind of properties are of this dark energy, what things we have to include in this term to make it work. So we know that, for example, dark energy is very homogeneous.
Right.
So that means it's pretty much the same everywhere.
Everywhere. And when we say everywhere, I mean, astronomers, cosmologists, their edition of the word everywhere means everywhere, like throughout the entire universe, which when you stop to think about that for a second, that's kind of extraordinary. The fact that you can have such a vast, unfathomably vast thing like the universe having the same energy density of this vacuum energy everywhere. It's kind of interesting.
It's really interesting. And it's completely unlike anything else we have in the universe. You think about dark matter. Dark matter is in specific places.
Yeah.
It's in the halos of galaxies. It's in galaxy clusters. We see it in concentrated clumps, but we don't see it just everywhere in space. We don't see it in the room around us, for example.
And that kind of draws out one of the differences, I guess. I mean, you said earlier on, dark energy, dark matter, they sound similar. They're very different things. Dark matter is still unknown exactly what it is, but the leading theories are it is some kind of stuff, right? It's new kind of particles or even old kind of particles, but we just haven't figured out how they work yet. It's something which we can get a grip on. Dark energy, we still don't really know what it is in any real way, shape or form, but the leading theories are that it is a fundamental property of space-time itself.
Yeah.
Right? It's built into the equations about the space-time that the universe exists in, which kind of helps to explain, at least to first order, why it would be the same everywhere. Because the laws of the universe are the same everywhere.
Exactly, yeah. So dark matter is not the same everywhere. Ordinary matter is clearly not the same
Definitely
everywhere.
not.
I'm very different sitting in this chair than you were sitting over there, right? Our densities are quite different. So, yeah, it's unusual in that sense, and it's very, very different. The other really key property is that it's not very dense.
Right, it's very, very spread out. It's
Now, we're being a little bit naughty here without explaining and sort of talking about energy and densities a bit freely. So let's just put that thought up front first.
Sure.
Energy and matter are interchangeable. So people like Chris and I tend to use those terms a little bit interchangeably.
Yeah, you get used to that in physics, in astronomy, in cosmology. And that, again, goes back to our friend Albert and his work on relativity. And the famous equation, E equals mc squared, is the simplest summary of that. Energy, matter get used interchangeably when we're talking about these sorts of things.
Yeah. So you can transform energy into matter and vice versa.
Yep.
They're kind of two sides of the same coin, if you like.
And equally importantly, energy interacts with gravity. Gravity works with matter and with energy. And so if you've got a lot of energy, it's kind of the same as having a lot of matter.
Yeah. So we can, for example, say take dark energy and we can say, well, it's not very dense. Well, how not very dense is it? Well, if you were to look at it from a matter perspective, you'd be looking at something like 7 electrons in a cubic centimetre of space.
Now, okay, cubic centimetre, that's not very big. Then again,
super big.
Electrons are very, 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 very small.
Tiny.
And so 7 electrons in a cubic centimetre is an extraordinarily low amount of matter.
Yeah. Electrons are so incredibly tiny, we just can't even... There's no way that we can detect something that's of that density, right? We're not going to be able to see a few electrons per centimetre cubed.
No, which is why you don't see the effects of dark energy between us here in the room, Emily. We're not,
No.
You and I are not slowly coasting apart across the room here as the space expands between us. But we do see it on cosmological scales, right? Very, very large scale distances between galaxies and clusters of galaxies. We see this effect because over very, very large distances, tiny effects build up.
Exactly.
To extraordinarily large, or at least measurable levels.
And whilst there might not be very much dark energy in 1 centimetre cube of space, it's the same in every single centimetre cubed of space in the entire universe.
Yeah.
So that's why it adds up to such a huge fraction of our energy budget, basically, for the universe.
Yeah, I mean,
it's everywhere.
You and I here on Earth, we see a lot of matter around us, but you don't have to go terribly far from Earth to get down to quite low levels of matter, even in our solar system, let alone...
Not very much at all.
No, very, very little, very little. And so, as you said before, the whole matter density is very variable throughout the universe. Got lots of it here, very little in most of the universe. Whereas dark energy is just everywhere, same quantities. And so it builds up and builds up and builds up, the effect of it over large distances. But you don't see it. We don't notice it at small distances.
Yeah.
Okay.
And then the third key property that we have to investigate with dark energy is that it doesn't appear to interact with any of the fundamental forces except gravity.
Right. And this is where it gets really quite tricky, because most other things, or at least matter, we're able to see around us really quite easily because there's lots of interactions with the other forces. We're able to see light being emitted by or bouncing off them.
Yep.
Or we get to see nuclear forces at play and detect them that way. But if it's only gravity, gravity is important, but on the scale of the forces of nature, it's very weak.
It's a very weak force.
Very, very weak. And if that's the only thing we've got, that makes it very hard.
Yes.
So it's incredibly low density and only using the weakest force of nature that we have. Good. Excellent. So that's a challenge.
Yeah. So those are the three sort of key properties that we know for sure about dark energy. And therefore we know that it dominates across the universe because we can make some observations that tell us things like how much energy there is in the entire universe, and then we can make observations about the other bits basically and fill in the blanks. So as an example, we know that from the supernova measurements that we discussed, that the universe's rate of expansion is accelerating.
Right.
Now, it turns out that if you look at the universe and look at these balances of forces, you end up starting to write an equation down where you're trying to balance the left-hand side of the equation with the right-hand side. This is basically saying, can you balance the push of the universe out from dark energy with the pull in from gravity?
Right. And that's really important because if you can't make those two sides balance, then what that's implying is either things should be rushing together really, really quickly or flinging themselves apart really, really quickly instead of what we see.
Yeah.
Which is pretty balanced.
And it's a little bit complicated because the two things, those dark energy and gravity, behave in slightly different ways. But we can get to a point where you can say, well, if we have this much density of energy in the universe, then we can find a happy medium, if you like, the tipping point of where there's going to be no change. And this is a density of energy called the critical density.
Okay.
And that's technically defined as basically the universe is going to completely continue expanding and then turn around and just exactly stop expanding at time equals infinity.
Right. Okay. So you can kind of intuitively see that. That's sort of the notion of after a big bang, everything continues to spread apart, but slows down. And on an infinite time scale, it just coasts to a nice gradual stop. And everything stops.
And obviously that's a really, really fine balancing point, right?
Yeah.
You have to have a really precise number for that. But we do know the critical density.
Mm-hmm.
It's something, I'm going to move to meters cubed here because it's slightly more easier to think about. It's something like 5 hydrogen atoms per meter cubed.
So what you're talking about is that would be the density required throughout the universe in order to just coast to that final point of, we're stopped, finally, at infinite timescales. It's, what is it, 5 hydrogens?
5 hydrogen atoms per meter cubed.
Okay. That's not a lot.
That's not a lot.
That's
but
a very small amount of matter.
Yeah, but imagine all the empty space there is in the universe.
Yeah, okay.
Huge galactic voids where there's just bubbles of emptiness, basically, in the universe.
All right. So if we spread everything out, 5 per cubic meter. Okay, that's our critical density.
That's critical density.
Right.
Yeah. So the first thing we can go out and measure, therefore, is what is the density of the normal matter, the ordinary matter that we can see, the galaxies, the stars, the people. We'll add everything up and see what that is.
And that's the easy part because we can see it.
Yeah.
We can see a lot of it. Yeah. So, okay.
Do big surveys and work out basically what that is.
Right. How'd that work out?
Well, we got to 0.25 hydrogen atoms per cubic meter.
That's not 5. That's quite a long way away from 5.
About 5%.
It's about 5%. We talked about that earlier. Yeah, 5%. Okay, good, right.
Okay, so, but that would be fine. Now, there's no reason why the universe, from just those two measurements, needs to be any different than what it is, right?
No.
That's fine. We can cope with that because we just say, well, we don't have enough matter to balance this, to get to this nice critical density, to balance the universe, so the universe is just going to keep on expanding forever.
Yeah.
Okay, we can do that. Then we go along to the next measurement, which is we use the cosmic microwave background. And the cosmic microwave background, we've talked about it in previous episodes. It's just such an amazing tool for cosmology because it gives us, it's this afterglow from the Big Bang, and it contains information about everything that's kind of happened in the universe since about 300,000 years after the Big Bang.
Yeah,
so
it's
basically not very long after the Big Bang.
Yeah, it's this really low-level glow from very early on in the universe that we detected. What was it, back in the 50s? 60s?
60s.
Yeah. We did a whole episode on this.
70s.
Go back and go back and have a listen.
Yeah.
But it's really, really valuable information.
Indeed. And one of the really key parts of pieces of information that we get from measurements from the cosmic microwave background is what actually is the energy density of the universe around us.
Right.
So we know the critical density has to be 5. We know that what we see in matter is 0.25.
Yeah.
What we see in the cosmic microwave background that tells us the total is about 5 atoms per hydrogen atoms per cubic meter.
Okay, so we know that it's about 5. We see 0.25.
Okay, so we need to go and find out what's going on in this.
Yeah.
This 95% that we're missing.
Where's that come from?
Okay, so the next measurement we can go at is to look at, basically we can look at galaxies, look at their redshifts. And there's a really, really important survey called 2DF, 2 degree field, which is basically we pointed telescopes outside of the galaxy. So we didn't try to look through the galaxy because the stars get in the way. It's really annoying. So if you want to look at things outside the galaxy, you point up, basically up out of the galaxy. Really, really deep survey. And it took years and years and years to put this survey together because it's hard data to get. Very, very distant galaxies. From the survey, it was very, very clever. We could basically work out how much matter in terms of both ordinary matter and dark matter existed in our local. And it's not even local. It's 2DF goes to huge distances.
And is this by, as you said, taking this really, really deep, long time frame look at bits of space and saying, okay, so how many galaxies can we see? How much can we see in there? But also, how are those galaxies arranged? Is that where the dark matter comes from?
Yeah.
That you need to invoke this weird dark matter, its gravitational properties, in order to be able to explain how all of these galaxies are sticking together in the way that they're sticking together. You have to have both of those elements. That's where that's coming from.
Exactly, yeah. And so then you get to this number, which is sort of 1 and a bit, about 30% of what we're looking for in terms of the total energy density.
Right, 1 and a bit out of the 5 hydrogen atoms per cubic meter is explained by the matter and the dark matter.
And dust matter, yep. So we have 5% from that matter. We have 30% matter, ordinary matter plus dark matter.
So that's where your 70%
and there's still
comes from.
70% missing.
Yeah. So we know that the universe has this density because that's what the cosmic microwave background measurements tell us, but we can't see it in anything else.
Exactly.
Right.
And I have to stress that these are not the only measurements. Like, we've gone out and done this many, many times using many, many really clever surveys. Another one that I absolutely love was a survey called the Wiggles survey. A lot of these surveys were done in Australia. I think they're quite keen on this idea.
I think they like the Wiggles down there. Yeah.
It's also Australia's well placed in terms of geography to look at this outside of galaxies.
Right.
Outside
Pointing in the right direction.
Galaxy, yeah. So they looked at another property, basically again looking at galaxies, but looking at the spaces between them and using that to measure distances in the universe, which was really clever. And we've continued to do supernova surveys. We've continued to refine measurements of the cosmic microwave background. We know the data extraordinarily well now.
So this is not a measurement error. This is not sort of, look, we forgot to carry the 2. It's not, but if we'd only just measured this other thing as well. Everything's pointing in the direction of the universe is full of stuff at a level of about 5 hydrogen atoms per cubic meter, and we can only see about 1.5 of them.
Yeah. And it's amazing. And we don't really have a good reason why we should be almost exactly at the critical density.
That is the other question. The first conundrum is, so where's the other 70%? What the hell is that? The other flip side to that is, why should we be at critical density? I mean, there's nothing particularly special about that at face value.
No,
we shouldn't be necessarily coasting off to an infinite distant future of everything just slowly, gradually crawls to a halt. We could continue to expand to forever. We could crunch back in on ourselves. All are possible within the theories. why would it be critical?
No, there's no reason. And actually, the first rule of cosmology is to basically assume that nothing is special. We are not special. We are not in a special place in the universe. Our galaxy isn't special. Our local group of galaxies isn't special. There's nothing that should say we should be at critical density.
And yet we seem to be very close to it.
Which I guess scientists like myself definitely interpret as there's something more fundamental there that we don't understand yet.
Yeah, that's, generally been a nice guiding principle, at least for the last couple of 100 years, is every time things look a little bit too convenient, it's probably because we don't get it yet. It's not because we are special. It's not because someone made it that way. It's because we don't understand the question yet. Okay, so let's gather. Let's gather our thoughts together. We have evidence. We have a whole pile of evidence that dark energy exists. It has to exist. We don't know what it is. We don't know where to find it. There's a whole bunch of theories out there, but none of them are completely compelling. None of them have solved this problem. Not only are we very close to this critical level, which is very, very difficult to explain, but the Nobel Prize in 2011 went for, it's going to keep, it's accelerating. It's not just coasting out. It's getting faster. Why? Where the hell is that coming from? We don't have any explanation for this. We don't know exactly what it is. It's a number that Einstein came up with, threw out, and then we brought it back together again. Emily, what's going on?
Okay, it's really confusing, but this is the forefront of science.
Yeah.
Like, we've only had this idea of dark energy for 20 years or so.
Yeah.
So it's not surprising that.
It's very, very new. and that's where scientists get excited, right? There's a lovely look that comes into the eyes of cosmologists and particle theorists and all sorts of people when they start thinking about this and going, well, clearly we don't understand everything yet. Let's go looking. It's like a treasure hunt. It's great. Yeah. Great fun.
But let's step through kind of the universe in time. Let's tell the story of our universe.
Okay.
Because now we've got this idea that dark energy is there. We can start to put that puzzle together and see at least what the observations tell us about the history of the universe.
Sure. Because, ideally, these ideas wouldn't just be bizarre sitting out on their own. They've got to fit in with everything else we've got. So, okay, walk us through.
Okay, so we've got Big Bang. Now, we've mentioned it a couple of times, maybe not gone into super detail. Maybe that needs to go on the board.
Yeah.
This idea that the universe expanded very, very quickly, very, very early on, like in the first few fractions of a second. We had this period called inflation.
Oh, and that's such a big topic for another time.
It's a big topic.
When you say it expanded quickly, this is off the charts. This is something like 10 to the 27 times within a tiny fraction of a second. That. Okay, we need to address that some other time. We can't even understand
those numbers. They're too big.
But let's just sum it up.
But it's an expansion. Right?
That happened.
So it's natural to think, well, we've got this thing called dark energy. Does that explain inflation?
No.
We have no idea. We have no idea if inflation is linked to dark energy or not.
So we have this very early on stupendous amount of expansion, and then now we've got this other kind of acceleration and expansion and we have no idea. Haven't got the foggiest. They could be completely separate.
They could be very, very different, or they could be similar things. Mm-hmm. They do the same job in the sense that they push the universe apart, but on very, very different scales, right? Different energy densities. So maybe.
Yeah.
Anyway.
They could be as different as gravity draws things together and positive and negative electric charges get attracted to each other. Similar kind of thing. Very, very different, at least we think.
Yeah.
So who knows? But, jury's out on that one. Yeah. All right, so that happened. The universe expanded and moving on.
Yeah, and so then it just sort of slowly grew over a period of several billion years. And then just as at the tipping point of what we would have expected to be now gravity is going to take over and start to contract down the universe, then it appears that dark energy starts to come into its own.
Right, okay. So this is not something which has been kind of dominating the entire time. You're saying that that balance sort of shifted after a very long, billions of years.
Billions of years. So about 5 billion years ago. So what are we, only about 8 billion years into the history of the universe, did we start to see, it's not exactly a switch on because we believe that dark energy was always there.
But the balance shifted.
Exactly. So it became much more apparent that dark energy was able to drive this expansion of the universe. And so the universe has been expanding at an accelerating rate ever since then.
Mm-hmm.
And it's really hard to get your head around, because when we think about densities and how these things work, if we think about matter density, right, this is a reasonably straightforward concept. If you've got 5 hydrogen atoms in a cubic meter and you double, and you have 2 cubic meters after expansion, you've still only got 5 hydrogen atoms.
So you've halved your density.
So you've halved the density.
Yeah, double the volume, half the density. That makes sense. You spread stuff out.
Yeah, but because dark energy is a property of space itself, if you double the amount of space you have, you double the amount of dark energy.
But that almost sounds like you've just, like, we know that the universe is expanding. And so that almost makes it sound like we're filling the universe with more and more energy. Where's that?
That's really hard, because it's not the total energy budget of the universe is not changing.
So we're not
creating energy.
We're not creating energy, but we are keeping the same energy density throughout the universe as the universe is expanding. Yeah, that'll do your head in.
Yeah, it does do your head in. But this is why, like, for example, when we say that the acceleration of the universe is currently expanding, but we expect that time is infinity to it to stop, because if you're accelerating in a car, you wouldn't expect the end outcome of continual acceleration to be stop.
Yeah, okay. So if we are observationally so close to critical density, right, that suggests eventually, long term, we're going to stop, slow down, or eventually reach that critical point of in infinite time frame, everything stops, and yet we're expanding with an accelerating rate. How does it? That doesn't work.
Yeah, no. So that's why dark energy is really hard to understand.
This is confusing. This is weird. All right.
Yeah. Okay, but let's take that now, the end point of the universe. So dark energy is happening, accelerating the expansion of the universe now, but at time equals infinity, it will stop. That's our current, because we're at critical density, that's the predicted outcome.
Okay.
Now, if you change the numbers by small amounts, like even within our margins of error that we're currently measuring the density of the universe, then the outcome for the end point of our universe is very, very different.
Very, very different. Okay. So if we change them one way, I'm guessing it is very different in one way. And if you change them the other way, it's a very, very different outcome indeed.
So if we end up with a density of the universe that's just a little bit less than critical density, either because you end up having a bit more matter or you have a bit less dark energy, then your whole universe will contract down and it will start to compress down as time goes on. So basically gravity will end up winning. It will pull everything together. And this is a scenario which we've affectionately called the Big Crunch.
Right. You have a big bang and then later you have a big crunch.
Yeah.
And it all comes back together again.
Yeah. So, and maybe the universe gets born again. I mean, this is a very psychologically attractive theory, I think.
Well, yeah, and it sounds good. It kind of fits with a whole bunch of different philosophies of things get reborn and recycled, and the universe itself gets reincarnated again as another. Who knows? Yeah. Interesting idea. Very speculative.
Whenever I ask for polls of my students and so on, we sort of talk about this, and I say, what we are at this tipping point, right? If what would you like the universe to look like? What would be your hope? And almost everybody goes for the Big Crunch.
Really,
they love the idea of a big crunch.
Isn't that weird? That there's a personal connection there, even though this is on time scales and space scales, which are so far beyond our puny lives, let alone the future history of the Earth. We'll be gone well and truly by then.
It may be because the other options are slightly unpalatable.
Okay, what are the other options?
So the other options is either we're exactly at the right point, which is a little bit like, why should we be at this exact
that raises
point?
a whole bunch of other philosophical questions.
That's weird.
Yeah.
Or the other option is we've got a basically under density of the universe. So that means that gravity is too weak to overcome
and dark energy
expansion.
wins.
Dark energy wins.
Which means it keeps accelerating.
And we get to a point called the Big Rip.
Ooh, that doesn't sound good. I mean, Big Crunch doesn't sound good, but Big Rip sounds somehow worse.
Yeah, so this is the idea that things move further and further and further apart. Now, we know that even in the current model, basically, as time goes on and galaxies move further and further away, we're going to stop being able to see them. But that will happen to even the galaxies that are nearby. If dark energy ends up being strong enough, it could even overcome the gravity that's holding galaxies together in groups. it could
So
overcome.
we lose the local cluster.
We lose the local group of galaxies.
But surely, I mean, if you take that to a logical conclusion, I mean, if dark energy means that it's going to accelerate, it's not just fast expansion, it's accelerating. That acceleration keeps going. Then eventually, surely, even the gravity within, like even the gravitational attraction within a galaxy gets overcome.
Yep. So then you start. So the sun's gravitationally attracted to the center of the galaxy, so we orbit it. But if dark energy becomes strong enough, then it could tear that apart, basically.
But
tear all
hang
the
on.
stars in a galaxy apart.
But next layer down is the solar system.
All the planets could be torn apart from the sun.
And keep following down this rabbit hole.
All of the objects on a planet be torn apart.
All the atoms within your body. Yeah. And like keep going down. You've got the atoms themselves. The fabric of space-time itself gets ripped apart. That's a big rip.
It's a very, very big rip.
Yeah. Effectively, dark energy would just completely destroy the fabric of the universe itself and everything in it. Yeah, okay, I'd take the crunch over that. I think that's... yeah, I mean, look, a future of a reverse Big Bang where everything gets incredibly hot and dense is not particularly palatable either. But you're right. Psychologically, I'd kind of go for that. There's something really quite terrifying existentially about a future of just everything being torn apart.
Yep. And we also call this the ultimate heat death of the universe. Because even if dark energy is not strong enough to tear apart even, say, a galaxy, eventually stars will run out of fuel, they'll die, there'll be no more energy input into a galaxy, no more energy input into a solar system. Everything will start to cool down. It'll eventually reach absolute zero, which is the coldest you can be. And there'll just be lumps of matter just drifting around. No light, no heat, no...
So even if
anything.
we don't get the big rip, it's still a fairly depressing end. Yeah, better to go out with a crunch than a whimper.
Yeah, and these are the wonderful things that we need to learn more about dark energy to understand why. And I think it's so amazing that we are on this tipping point. Maybe we are at exactly this critical density.
Which is an interesting question because we need to know why.
We need to know why. Or maybe we're a little bit over. Or maybe we're just a little bit under.
In which case, it would be really interesting to know how, which way are we going to go ultimately. I mean, we won't be there, but it's such an amazing existential question. What's going to happen? Well, with brain reeling from that one, I mean, in a way, I want to know, and in another way, I really don't. Like, it feels very, very comfortable to be here on Earth with the sun shining through the window, thinking, I don't have to worry about the ultimate fate of the universe, whether or not it's all going to crunch together in a huge, fiery ball of death, or whether or not it's all going to be completely torn about by dark energy out of control. Who knows? Do you have what would be, if you had to put £50 on the table right now, Emily, which way would it go?
I think we're right at critical.
Yeah?
Yeah, I think there's something there we don't understand. I think it's too weird that we're too close.
Does that imply a big bloke with a beard looking down and fine-tuning it? Interesting question, which we won't delve into. But yes, there we are. We need to finish it there. Because, look, we could rabbit on about this for a very, very, very long period of time. But we're not going to, because we need to come out of this episode. If people want to get in touch with us with their own existential questions about the universe, Emily, how do they do that?
So you can grab us at SyzygyPod on Twitter.
You can.
In fact, SyzygyPod is kind of our hashtag everywhere you want to go.
It is our nom de internet.
Yep.
At SyzygyPod. So you can find us on Twitter, on the Instagrams.
Facebook.
Yep. And in fact, we've got a webpage as well.
Woo.
Because we're old school like that. Syzygy.fm. You can find all the old episodes, all the show notes, all the pictures, everything. As well as a contact form. So you can just send us a little note. Say hi. Yeah.
And send us your questions, because this episode blows my mind, and I always end up with about 6 different questions that I need to go up and look up. So I'm sure everybody out there has another 10 different questions as well.
Yeah, if it's a question about the ultimate death of the universe, or indeed anything else to do with astronomy, send it our way and we'll have a look at it. And if we have any interesting things to say about it, then we might feature it on a future episode. If you would like to get involved and help the show, there are a bunch of different ways that you can do that. You can give us a review. Go and just give us some stars and a couple of words on your podcast platform of choice. It really helps us to rise up through the noise and allows other people to come and find us. The other thing you can do, of course, is to tell all of your friends and family. There's this amazing podcast that I listen to where these two people natter on about the universe and stuff, and it's cool. Do that, because we'd love as many people to listen to us as we can possibly find. So listen, we will catch you again next time. We're going to be recording something off the mystery list that has disappeared off the board in the next episode. And again, don't forget, we've got a live show coming up 22nd of November up in Thirsk at the Podcast Social Club, the first one of these that they're running. So if you're in the area or if you feel like traveling, come and see us. It's going to be a great time. But until then, we'll catch you next time. See you later, Emily.
See you later.
Bye.